Hello students, I am Dr. Kulvinder Singh taking the first lecture of generic elective course, and this course is on mechanics. We are starting with the unit 1, which is a mathematical recapitulation of what already you have studied at your school level. Now there are two sections of this unit. One is on vectors and the other is on ordinary differential equations. So let's start with the vectors today. Now which physical quantity is a vector quantity? For this we have this concept that a quantity which possesses, number one, a definite magnitude, an appropriate direction, and obeys vector rules. If these three important properties are there in a physical quantity, we call it as a vector quantity. Examples: number one, velocity, acceleration, force, momentum, torque, and number of quantities are there, etc. you can write. So these quantities are the vector quantities. It means if I have to define the velocity, I have to provide a magnitude and I have to tell that what is the direction of the velocity, and this quantity obeys the vector rules. That's why this is a quantity which is categorized as a vector quantity. Similarly, others also. Now the second important point to understand is how to represent a vector. Now in a simple way, a vector can be represented by any symbol. Say for example, I am using this symbol for the force. This must have a magnitude. It has a magnitude, say F, and also has a appropriate direction. And let me call this direction by putting it r cap. R cap actually represents a unit vector, so that gives a direction. So this is normally a mathematical relation for a vector quantity. But vector can also be represented in a graphical manner. So there is a graphical representation. Graphical. Say, let's take an example to understand this. Suppose I have a force which is equal to, say, 24 of Newton and is in direction 30 degree north of east. Now this is the vector quantity because it has a magnitude and also has a appropriate direction. So how to represent it? So first of all, let's take the reference directions. Let's say this is the east direction and this is the west direction. This is north and this is south. The geographical direction, and they are perpendicular to each other. Actually, I am showing it on a vertical plane, but they are both these directions, they are in a horizontal plane. First of all, if I have to represent it graphically, I have to make a conversion relations. And what this relation is, say for example, I choose 1 centimeter to represent 3 Newton. So this is my conversion relation. I am not using the equal sign here. It is equivalent sign. That means 1 centimeter of length shown graphically to be taken as 3 Newton. So obviously this is 24 Newton. So I have to draw a line of 8 centimeter. And direction, it says 30 meter north of east. That means from east it should be at an angle of 30 degree. So I have to draw a line which is of 8 centimeter equivalent to 24 of Newton, making an angle of 30 degree with the east direction. So this is going to represent the quantity force, which is 24 Newton and is in the direction 30 degree north of east. Now we know from the point of resolution, already we have studied in school level, that if I have a vector making an angle of theta, say with the x-axis, and there is a y-axis also and it is in the xy plane, I can always resolve this vector. Say this vector is a vector which is having a magnitude a. Its x component is going to be a cos of theta and y component is going to be a sine of theta. You can obtain this from trigonometric relation. Now this vector a can also be represented in an analytical manner as you take this component a cos of theta and put a unit vector I cap. This is only a part of this vector. Add to it a sine of theta j cap, with the understanding that when I am putting a I cap, this is a unit vector along x-axis, and when I am putting a j cap, it is a unit vector along y direction. So I can write a vector by this type of presentation also. We call it as an analytical presentation. So this is also a way of presenting it. Sometimes what we do is we put it in this way. Say for example a vector is AB vector. Now when I am putting it in this way, it means its starting point is A. Say this point is A somewhere and this point is B. So the first one is a starting point of a vector and second one is a terminal point of a vector. So this is the vector which I am representing as AB vector. Please note down one thing. This particular arrow is only a marker which tells us that the quantity is a vector quantity. We should not confuse this marker with the actual direction. Actual direction can be any direction. But for representation, we normally put a horizontal arrow, right? Starting from A to B. That's all. So it's only indicator, but this is actual vector. Actual vector can be in any of the direction. So this is how the vectors are represented. Now next we are taking that how we can do the algebra of the vector. Algebra means that how can we add vectors or we can subtract vectors. Later on we'll study also the multiplication of the vectors. So let's start with, first of all, the concept of addition of two vectors. Addition of two vectors. There is a graphical method which is sometimes called the law of parallelogram. Law of parallelogram. Suppose you are given two vectors. Say this is vector A and there is another vector, vector B. And we are asked to find out the vector A plus vector B. Let me call this now as a vector C. So graphically what we can do is, we can take these two vectors as the two adjacent sides of a parallelogram. This is A vector and say this is B vector. While I am putting it here, I must keep one thing in mind, that the direction of these vectors must be the same as the direction given to us, and their length must also be maintained. Now what you do is, this is B vector, complete the parallelogram, right? Then the vector starting from the common origin and going to the other end, this diagonal, is your C vector. This is the law. Now same thing can also be taken in an analytical way. How? Look at this. Is A and this is B vector, and let us say this angle is theta. That is the angle between A and B. Now this vector C, which according to the law is a diagonal starting from the common point of A and B, this one, it has a magnitude given by the formula A square, where A is the magnitude of the vector A, plus B square plus twice of AB cos of theta. This is how we can write the magnitude of this vector. Now if I have to give the direction, I can take the reference vector either be a vector or B vector. Suppose I take this as the A vector reference, that means I am giving the angle between C and A. Let's say that is alpha. So to get the value of the alpha, the formula is that tan of alpha is equals to B sine of theta divided by A plus B cos of theta. You can also give the direction taking B as a reference. If you do that, let me say this angle is beta. So we have a formula tan beta is equals to A sine of theta divided by B plus A cos of theta. So this is the law, which is the law of parallelogram. This is the magnitude, the formula for magnitude of the resultant vector, and any one of them you can use to get the direction of the resultant vector. Now the next point we are taking is the subtraction of the two vectors. Let's take the how to subtract two vectors. Subtraction of two vectors. Now subtraction of the two vectors, that means if I am looking for A vector minus B vector, I should treat this as A vector added to minus of B vector. This is a mathematical relation for it. When I say minus of B, this vector has the same magnitude as that of B, but has the direction just opposite to B. Rest we have to process it in the same way. Now in a parallelogram, you take A vector. Instead of taking B vector, let's take the negative B. This is minus B. Once again you complete the parallelogram. Then this diagonal, which is starting from their common point, that is A and minus B. Let's say this vector is D vector. This diagonal is going to give you the difference of the two vector, or you can subtraction of the two vector, A minus B vector. Let's look it from the analytical point of view. Now we just have discussed that the vector between A and B is, angle between A and B is theta. But this time we are taking A vector and negative of B vector. Although negative of B vector has the same magnitude as that of B. So as far as magnitude part is concerned, even the negative B has the same magnitude. But this time there is a small change which you have to remember. If the angle previously was theta between A and B, between A and minus B, this is going to be 180 minus of theta. Rest you have to go in the same way as for the addition of the vectors. That means if I have to look for the magnitude of D, this is going to be A square plus B square plus twice AB, but this time it is cos 180 minus theta, because now the angle between A and minus B is going to be 180 minus theta. Since the magnitude remains the same, so there is no negative sign here. We have A square plus B square, but because of this cos 180 minus theta, as you know, this is negative of cos theta, so we can modify it to A square plus B square minus 2AB cos of theta. And similarly, we can go for the angle also. If this is my D vector and I have to define the angle this time say with A. So the formula for this is saying that tan of alpha is equals to, previously it was B sine of theta, but this time it becomes B sine 180 minus theta, and this is equals to A plus B cos 180 minus theta. You can modify a little bit saying that this equals to B sine of theta, as sine 180 minus theta is sine theta, but cos 180 minus theta is minus cos theta. That's why this becomes A minus B of cos of theta. So you can use this relation to find out the angle between the subtraction of A and B, that is D vector, as tan of alpha. Similarly, you can do it for the angle with B also. Now, if you are asked to find out the addition of say many vectors, and for simplicity I am taking the 3 vectors at this time, or you can extend it to many vectors also. So again we have 2 methods. First of all, let's say this is my A vector, this is my B vector, and let's say this is C vector. And we are looking for the first of all the addition. So graphically we can write it as A vector. Now this time there's a small change. You do not show the B vector from the common origin. You start the B vector from the terminal point of A. So this is B vector, and then we have, this is C vector. So once you complete this, then the resultant of this, starting from the initial point of first vector, that is A vector, and terminating at the terminal point of last vector, this is going to be A vector plus B vector plus C vector. So we can call this as, let me call this as R vector. So this resultant of A, B and C, this law is called law of polygon. Now how to do it analytically? There are 2 ways again. You add A and B first of all, get the C vector, then that vector is to be added to the third vector, but this is the lengthy method. Let me say if they are coplanar, we have a simplified method also. First of all, you take the reference direction, say this is x direction, this is y direction. Now you plot all these 3 vectors on this plane, having their origin common to the origin of the coordinate system. Let me say this is A vector, this is B vector, and this is C vector. You must be given the informations to find out what is the angle between the A and B, or you can say with the x-axis and B, and similarly say this angle is theta 2, again with the x-axis but on the negative side of it. So you somehow will be given these informations, and you are asked to get A vector plus B vector plus C vector. Let's say this is R vector. How to do it? So to find out the magnitude of R, we have to do a little bit of work to find out first of all the component of all the vectors along x-axis. Remember, when we take the component, if the angle is theta, the component is going to be the vector magnitude and cos of theta. But since A is purely along x-axis, so is going to contribute completely to it. Even if I write A cos of 0, cos 0 is 1, so it is going to be A. But for B, the component is going to be B cos of theta 1. That is along x-axis. The component of the B along x-axis is going to be B cos of theta 1. Similarly, you go for C, but this time it is on the negative x-axis, so this is going to be C cos of theta 2. You calculate first of all this. Similarly, you calculate the y, total y component of all these vectors. But since x is purely along, a is purely along x-axis, so it's going to give you 0 along the y direction. What about b? B will give you b sine of theta 1, and c, since again its component in y direction is negative y, so we'll write this as minus c sine of theta 2. Once you get this, if there are 4 vectors, you have to do again for 4 similar things. But once you get this, your resultant magnitude is going to be under root of x square plus y square. I'm not writing here the cos of angle between x and y, since component x and y, they are at 90 degrees, so cos 90 is 0, so that part is not to be written. Now if I have to find out the angle of the resultant, say with the x-axis, this is going to be y by x, and if we have to get the angle with y-axis, this is going to be x by y. I am using the modulus sign here because of a reason. If both of them are positive, the direction is to be taken in the first quadrant because x is positive, y is positive. So ratio also is positive. But if both of them comes out to be negative, right? This ratio is going to be positive. But this time you have to take the final vector in the third quadrant. So what we do is we calculate the angle by taking the modulus of it and decide that which quadrant of this graph is having our resultant vector, that we choose by finding out which of the two is positive or negative, or is it by that both are positive or both are negative, we choose it. In this case both are positive, in this case y is positive but x is negative, both are negative for third quadrant, and in this case x is positive and y is negative. So this way we calculate the direction part. So students, let's take the multiplication of two vectors. There are two types of multiplications. When two vectors are multiplied together, they can lead to a scalar quantity or a vector quantity. If they lead to a scalar quantity, we call it as a scalar product. Scalar product. Or sometimes it is also called the dot product. It means that if two vectors, say A and B, they are multiplied together and they give you a scalar quantity which do not have any direction, we call it as a scalar product. You can rewrite this as A dot B is equals to magnitude of A, magnitude of B, and cos of the angle between the two. Now the vector A and vector B, when are multiplied together having an angle theta, you can write the product in this way. There is another way to look at it. If I take the projection of B on A, that is going to be B cos of theta. So this is basically is a projection of a vector B on A. That means the magnitude of A multiplied by the projection of the second vector on A. That is the dot product. You can also express it in component form, like you can write like this: ax equals a vector is equals to ax with the component along x-axis I cap, y j cap, a z k cap. And similarly you can write b vector also in component format: by j cap, bz k cap. And when you multiply the two vectors, say a dot b, that means ax I cap, ay j cap, az k cap, and is multiplied by bx I cap, by j cap and bz k cap. Now in order to simplify this, we have to remember certain rules. See, I cap dot I cap is equals to j cap dot j cap is equals to k cap dot k cap and is equals to 1. You can get the explanation from this particular definition, because angle between I and similarly j and j and similarly k and k is 0, so cos 0 is 1, so that's why it's 1. But if it is going to be I dot j dot k, or say I dot k, that goes to 0. It means when you have dissimilar unit vector along the x-axis, y-axis and z-axis, then you are going to get 0. So if you multiply it, you will notice that a dot b comes out to be ax bx plus ay by az bz. So respective components are multiplied together. In some situations, suppose the z component is not given to you. You treat the component to be 0 and use it in this particular relation. There are certain properties of the dot product, and that is first property. If you interchange a and b, that means you can take a dot b or you take b dot a, is not going to matter. We call this property as commutative property. Commutative property. The second important property, if I have k multiplied with a and is taken a product with vector b, this is equivalent in saying that it is k times a vector dot b vector. Similarly, if you have a vector dotted with a vector, this is going to be the square of the magnitude of the vector a. So these are some of the important properties which you can keep in mind while solving the problems. But this is very important. I dot I, j dot j, k dot k, that is always equals to 1. But the similar unit vectors, whenever it is taken as a dot product, they always give you 0. The other vector multiplication is called the vector multiplication. In this, when two vectors are multiplied together, they give you vector quantity. We call it as vector multiplication. Or sometimes we call it as a cross multiplication. If two vectors are multiplied so that you get a vector quantity, this is a vector multiplication. Now, this A cross B can be written as magnitude of A, magnitude of B, sine of theta multiplied by a unit vector which is perpendicular to both A and B. That means if you have A vector and B vector and the angle between the two is theta, the magnitude of the cross product is AB sine theta, but it is in the direction which is perpendicular to both A as well as B. It is something like this: A vector, B vector, and this is the resultant vector. This obeys the right hand grip rule. You take it in right hand way, that is, you turn your fingers from A to B, then thumb is going to represent the direction of A cross B, or you can write the unit vector which is giving you A cross B. If it is expressed in component form, for example, A vector if is given like this: AX I cap, AY j cap, AZ k cap, and B vector as BX I cap, BY j cap, BZ k cap, then in order to obtain the cross product, that is C vector, which is equals to A cross B, you can solve it this way. Write first of all ijk in the determinant form like this. Then first vector is A, so write its component first of all, and then B at the second place. So Bx, By, Bz. Rest is a solution of it, as you all know, that this can be written as I. Leave this row and this column and multiply Ay and Bz like this. That means this becomes Ay Bz, and then subtract the other multiplication, that is By Az. Now the next time you have to take this column out, then is minus of j cap. Notice that there is a negative sign here. Multiplication is done in the same way. Ax Bz this time. Means take the remaining components. Leave these. Ax Bz. And then Bx Az with minus sign. Now the third one is with the positive sign. Look. First one is with a positive sign, second is with a negative, and third one is with a positive sign. But this time, this column is to be ignored. And this is now Ax By minus Bx Ay. So this is how cross product can be obtained. There is another rule which you should remember. If you write ijk this way and going in the clockwise direction, use positive sign. Going in the anti-clockwise direction, use negative sign. What does it mean? It means if I write I cross j, this is positive k. Take the third one, but with positive sign. Similarly, if you take k cross I, this is again in a clockwise direction, so this is plus j. But if you go like this, j cross I, say, this time we are going in the anti-clockwise direction, the third vector is k, but taken with a negative sign, and so on. So these will help you to find out the cross product of the two vectors. Let's take some of the important properties of the cross product. The very first property is anti-commutative property. That means if you take the cross product of the two vectors and you change their position, you have to use a negative sign to it. So we call it as the anti-commutative property. This is called anti-commutative property. The next is same. You take k vector cross b vector, it still is equals to k a cross b. But if you take a vector and cross it with a vector, this is going to give you a zero vector, because both are in the same direction, so sine angle between the two will be 0. So sine 0 is 0, that's why 0. We are putting this arrow just to indicate, because the vector product ultimately is going to give you a vector. This also is a vector, we call it as a zero vector. So these are the relations which help you to find out the cross product of the two vectors. Now let's take the mixed multiplication of three vectors. Again we have two types of these multiplication. One is giving you a scalar quantity, and another one will give you a vector quantity. If you are given three vectors, say a vector, b vector and c vector, and you are taking the triple product which is going to give you a scalar, this is something like this, that you take a dot with the resultant vector product of B and C. This resultant, when it's taken as a dot product, obviously is going to give you a scalar quantity. Let it be D. The physical interpretation of this is that if you have these vectors, A vector, B vector, and say the C vector, this product is going to give you the volume of the parallelepiped which we are getting by construction in a repeated manner. So the volume of this parallelepiped is basically A dot B cross C. To find out the value, what we do is we take it like this. This B therefore is equals to AX, AY, AZ, BX, BY, BZ, CX, CY, and CZ. This determinant can be simplified the way we have discussed in the previous part. So this is going to give you the scalar triple product. We also have the vector triple product of the three vectors, which gives you a vector quantity. Once again, if you have A vector, B vector, and C vector, and you take the cross product of A with the cross product of B and C, this is going to give you a vector quantity. Now, in order to find it out, we have to simplify it. This is equal to, look, there is a way to write it. You write it in order in a clockwise manner. It started with A, then you write B, take a multiple of remaining but not changing the order. You started with B, take C and A, C dot A minus, we are going in a clockwise manner, we have taken B, now we have to take C, C vector, and the remaining are A vector dot B vector. You have a flexibility to change it because dot product, as you know, is commutative. I can write it as A dot C, there is no problem. But remember, this sequence is important. To solve this, which is C dot A is going to give you a scalar quantity, we know how to solve it. Then we have to multiply the value we are getting with all the components of the B vector and so on and so on. So this is how the cross product of three vectors can be taken, or you can say the vector product of three vectors can be taken. So students, by now we have learned that physical quantities can be a scalar quantity or can be a vector quantity. Scalar quantities have no direction, whereas in vector quantity, direction is a very important parameter for their definition. Let's take one real example to understand this. I am taking the example from gravitation. Let's take a very simple situation where we have a point mass m and there is nothing in the surrounding. It is in the space. And you are interested to know the gravitational potential at the point P, which is at a distance r from it, and let's say the value is V. The value V is given by the formula minus Gm by R. The negative sign is because of the attractive nature of the mass m. In fact, it is not only at this particular point. If I try to construct a spherical surface such that the point P is on the surface, everywhere we have the same potential. So we call this as the equipotential surface of the value V. Now if I choose another point, say Q, somewhere in the space, Again, I can calculate the potential if I know the distance between the point and the point mass m. And also, I can always think of a spherical surface around m where the potential is V plus dV, which is given as V plus dV equals to minus Gm by R plus dr. Alright? Potential is a scalar quantity, no need for any direction to define it, it has only value. But we can also associate another important quantity and we call it as a gravitational field intensity. At the point P, this is towards the mass m and can be given as Gm by R square and a unit vector, and this unit vector n cap is towards the mass small m. Similarly, I can always say the electric field at this point is minus Gm by R plus dr whole square, and I can choose another unit vector towards this mass m. This is a scalar quantity and this is a vector quantity. Can we have a relation between them so that once I know the potential distribution, I can come to know the electric field intensity? Yes, there is a relation, and this relation is that the electric field is equals to minus dV by dr r cap. But this particular relation, which says that the position derivative of the potential with a negative sign is linked to the electric field, can be applied only for one dimension, 1D. But in fact, this situation is a three-dimensional situation. What does it mean? It means that if I have to define the position of this point P, I have to give x coordinate, y coordinate as well as the z coordinate. But obviously at point P, at point Q, the coordinates are different, say x plus dx, y plus dy and z plus dz. So how to deal when you have three-dimensional space and where we are looking for this similar type of a relation between them? So here is the importance of what we call as a partial derivative. To understand the concept of the partial derivative, let us take an example of a hill. The horizontal surface is formed by the two axes, x-axis and y-axis. In fact, y-axis is coming perpendicularly outward from the board. Right? Now if I move from one point to another on the hill, obviously I can find that there is a change of the height. Now to get the relation for the variation of the height with the position, I choose a point P here, which is having a coordinate x and y. So this is the height. Let me call this height as h. Now if I move a little bit so that I reaches to a point which I am showing just for the sake of convenience, this is a very small displacement. Of course, on the diagram it appears to be large, but just for the understanding sake, this is x plus dx and this is y plus dy. Obviously, I find that there is a change of height, say h plus dh. So one can say easily that height parameter is a function of coordinate x and y. When coordinates are changing, there is a change of the height. So mathematically I can write that h is a function of x and y. Remember, h is a scalar quantity, right? So we are dealing at this stage with the scalar quantities. Now if I have to write down the variation of the height, that means I am looking for this at dh. I have here, when I start going from the point P to the point Q, I find x is changing, y also is changing. But There is a simple way of handling it. You do like this. You write down the variation of the h with only x parameter, with the understanding here that I will keep the y constant. That means if I change only the x coordinate and looking for the rate of change of height with this x coordinate only, where the other coordinate y is kept constant. So this gives me the rate of change multiplied by the net change which I have for the coordinate x. Similarly, I can do the rate of change of the height with y, but again in this case I am keeping the x constant and then multiplied by the net variation in the y coordinate. So this is an easy way of writing the variation of height by knowing the rate of change of the height with x coordinate and y coordinate, but in steps. In this case, I keep y constant and I take this derivative. We call this derivative as the partial derivative of h with x. And similarly, this is the partial derivative of h with y. So these partial derivatives actually help us to get the variation, because in space we have all the three coordinates. They may change. Maybe it's quite possible in certain cases one or two may remain constant, but in general all of them may change. So we have to take the change of the physical quantity with the space variation by taking all the variation with x coordinate, with y coordinate, as well as with the z coordinate. Now let's take more general situation where a scalar quantity depends on all three coordinates, that means x, y and z. Let's say the quantity v, which is a scalar quantity, is a function of x coordinate, y coordinate and z coordinate. Now I am looking for the variation of this quantity when I am changing my x, y and z. So partial derivative tells you can write this as dv by dx, but when I write like this, it means I am taking only the variation of v with x but keeping the y and z constant, multiplied by net variation in x plus the variation of v with y coordinate only, where x and z are kept constant, multiplied by the net variation in y, plus dv by dz multiplied by the net variation in z. So in this case I am keeping the y and z constant, and in this case I am keeping the x and z constant, and when I write this I am keeping x and y constant. Now this particular variation can be written in a slightly modified manner. You can check it yourself. I can write it like this: I partial derivative operator with x plus j partial derivative with y k cap, the unit vector along z axis, and partial derivative with z, this particular thing operating on v dotted with dx I cap, dy j cap and dz k cap. In fact, this is giving me the displacement vector when I am changing my position. Now if you take a dot product of the two, you will get back this equation. You can check it yourself. We have to multiply and you will easily get it. Now this particular operator is named as del operator or nebula, and the symbol we use for this is an inverted triangle with an arrowhead, and if it is in a printed form we normally make it bold. and we don't use the arrow in that case. So the variation of the dH can be written as the nebula operating on V multiplied by the displacement, which now I am showing as dr, with the understanding that the dr vector is equals to dx I cap, dy j cap, dz k cap. Now this particular term, that is nebula on V, that is nebula operating on V, is called gradient of V. This is named as gradient of V. This is a vector quantity. This is a vector quantity which involves the variation, right? As you have seen that there is a rate of change, that is the variation. This particular quantity, that means we are able to change the scalar field, which is in terms of V, into the vector field when it is written as a gradient of V. Now this gradient of V has its direction, which is in the direction of the maximum rate of change. Right? This is the important point, that this is in the direction which is the maximum variation of the physical quantity. Students, I have written one equation relating the gravitational field intensity as position derivative of the gravitational potential and a unit vector n cap. But as I told you, this is for one dimension where the variation only is on a line. But in general, with the understanding of this gradient, now we can write the gravitational field intensity is equals to minus gradient of V. That means this is minus I partial derivative d over dx plus j d over dy k d over dz operated on V. Once you do this, automatically the direction part is taken care of. So this is the equation which is a three-dimensional relation and can be used for finding out the vector quantity like the gravitational field intensity if I know how the gravitational potential is changing in space. So students, now you have understood that there is a differential operator, especially for the space differentiation, which can be written as nebula or del and is mathematically has this type of a shape. And we have seen in the previous section, when we operate this nebula on a scalar quantity, we are going to get a vector field or vector quantity. Can we operate this particular del operator on a vector quantity? Yes, but we can do it in two ways. I can operate this on a vector quantity. Say the quantity is a vector. In one case, I am going to get a scalar quantity. That means if I take this operator in this form, that means I am taking a dot product of this operator and the vector quantity, I am going to get a scalar quantity. We call it as a divergence of a vector. But I can operate it this way also. Take this del operator in this form as a cross product with a vector A. Obviously, this is going to give me a vector quantity and we call it as a curl of A. So you can operate nebula on a scalar quantity giving you gradient of that quantity. But when it is on a vector, it is done in two ways. One is called the divergence of A, where we have a dot product between this operator and the vector quantity. And the other method is where we take the cross product of the two, that means the operator and the quantity. Now let's take the divergence and curl of a vector quantity in detail. First of all, we are taking the divergence of a vector quantity. Again, let's take a real situation to understand this. I have a point mass in space with no surrounding. If I make a spherical surface around it, I notice that the gravitational field lines can be drawn in this manner, as it is an attractive field. So we have the gravitational field lines are pointing inwards. Now there is a concept where I take a small elemental surface here, say having a direction perpendicularly outward, and is represented as ds, and this is the gravitational field intensity E. So if I am asked to find out the net flux of these gravitational fields which are entering into it, I will write this net flux as E vector dot ds vector over a closed surface. Now if that is to be taken per unit volume, we name this quantity as divergence of E. And as we have seen, this divergence of E can be written mathematically as the nebula dot E vector, or we can write as I d over dx plus j d over dy k d over dz. Please notice that when I am writing d, I am taking a curve notation to indicate that these are the partial derivatives, and then it is to be operated on E, which may have this dot product here, Ex I cap, Ey j cap, and Ez k cap. Since it is a dot product, so can easily be written as d over dx Ex plus d over dy Ey plus d over dz Ez. So this is how the divergence is taken. So if it is coming inward, the net divergence is taken as negative. But if you have these field lines, say for example in electrostatic, when we have a positive charge, the electric field lines are going outward, then electric flux in that case is taken as positive. But here, since it's coming inward, so it's going to be negative here. So divergence actually gives you an idea that how a physical quantity is diverging out in space or coming from space. So if it is coming from the space, it is negative. If it is going outward, it is taken as positive. And if you have a very interesting situation, say for example, I have the field lines like this, and I now make a spherical surface, then you can notice that equal number of the lines are entering into this surface and equal number of them are going out of it. So if I have to write down the divergence of say this field which is A, the divergence of this field A is 0, because neither they are going in nor they are going out. So such a field is called solenoidal field. This is a name given to a field for which the divergence of that field is 0. In this case it is negative, but for the positive charge case that is positive. That depends upon what type of the field we are dealing with. Now let's take the next operation when nebula is operated on a vector quantity in a cross product form, and we call it as a curl of a vector quantity. This is written as nebula crossed with E, or you can say this is the curl of E vector. To obtain it analytically, we can write this as I, J, K, that is the unit vector along x, y, z axis. Then from the nebula, d over dx, d over dy, then d over dz. Since it crossed with E, Ex, that is the x component of gravitational field E, y and z. So this is how the curl of E can be obtained analytically. What is its physical significance? Let's take again the example of that point mass in space, nothing is in the surrounding, and we take a closed loop around it, a small one, which is covering an area, say ds. The small loop, I have shown it a bit to just give you an understanding. Now because of this mass, there is a gravitational field pointing towards this point mass, that let that is equals to E. Take a small length element dl, and when you take the line integral of this gravitational field over this whole closed loop and divided by the surface element, this is nothing but is the curl of E. I'm not giving the proof of this because this is a physical understanding of the curl of the field, any vector field. The line integral per unit surface area and its direction is governed by the right hand rule. Let me take some of the examples of it. Say for example, I have the curl of the field. Say this is one of the field. So we use the right hand to find out its direction. So this is the direction of this type of a curl. But if it is uniform one like this, there is no curl. So we can say the curl of this quantity is 0. Such a field is called irrotational field. So if you are asked to find out whether the field is irrotational, take its curl, and if you get the value as 0, then you can say the field is irrotational. Now to understand this curl part, let me take another example. Say I have a viscous fluid moving in a canal. We know that because of the viscosity, the velocity of the layers, the laminas, continuously keeps on decreasing as you move inside the liquid depth-wise. So if I keep this type of a wheel in it, you will notice that because the velocity is more on the top, so when the velocity is more on the top, so we get more rotation on this side, that is on the clockwise side. But because it is also having some of the layers influencing it, from the bottom, but they have less velocity. So ultimately you will find that this wheel will rotate in this manner. This is more because of the higher velocity, but this is less, so ultimately the movement goes like this. So when it is going this way, we say that the curl of this movement is having a direction perpendicularly inward. So to find out the direction of the curl, one thing is important, you have to keep this wheel in the maximum rotation part. But if you try to rotate it a bit like this, then you will notice that its rotational effect will continuously keep on decreasing. So to find out the direction of the curl, we have to keep it in a maximum rotation state. Now let's take the first numerical. Now this numerical is to find out the angle between the two vectors. We know that if I take dot product of the two vectors, it is going to be magnitude of A, magnitude of B, and cos of the angle between the two. This relation we'll use to find out the angle between the two vectors, that is A dot B vector divided by the magnitude of A, magnitude of B. Now to get this A dot B, let's put the values 2i cap plus 2j cap minus k cap as A dotted with 6i cap minus 3j plus 2k divided by the magnitude of both the vectors. To find out the magnitude, we'll take the relation that x square plus y square plus z square, then under root, that means 2 square plus 2 square plus minus 1 whole square. Similarly, we'll go for the b also. 6 square plus minus 3 whole square plus 2 square. Now for dot product, the respective components are multiplied this way. So we'll have 2 into 6, that is 12. Then 2 minus 3 will give you minus 6. And minus 1 and 2 will give you minus 2. And in the under root we have 4 plus 1, that is equals to 9. And this will give us 36 plus 9 plus 4. Simplifying it will give you 4. This will give you 3. And this then 36 plus 4, 40 and 49. And that is equals to 4 divided by 3 into 7. That is 4 by 21. So your answer is theta equals to cos inverse of 4 by 21. And if you simplify using your calculator, you will get the value as 79.02 degree. So this is the answer for the question number 1. It is important that if I get the numerator as 0, obviously the theta comes out to be 90 degree in that case. So this particular relation can be used to find out whether the two vectors are perpendicular to each other or not. If question is like this, that two vectors are given and they ask you to find out whether they are perpendicular, you just simply take the dot product. And if you get the dot product as 0, it means the two vectors are perpendicular to each other. And if angle is required, you follow this particular method. Now let's take the second numerical. This numerical requires us to show that the given three vectors are coplanar. To answer this question, we'll use the formula A vector dot with B cross C, that means the mixed multiplication, that is the scalar multiplication of three vectors. If it comes out to be 0, then definitely all the three vectors are coplanar, because the scalar triple product gives you the volume of the parallel pipe which has the adjacent sides as A vector, B vector and C vector. If all of them are in the same plane, obviously they will not cover any volume at all. So let's take the A dot B cross C and we'll show if it's possible this equals to 0, then we'll prove that this is coplanar. To know this, first of all the component of A, which is 1, 2 and 3, the B1 is 4, 5 and 6 and C is 7, 8 and 9. Let's simplify it. 1 multiplied by, leave this row and this column, this is 5 multiplied by 9 minus 48, then minus 2, leave this column, this row, 4 multiplied by 9 gives you 36, minus 7, 6 are 42, plus 3 multiplied by, leave this column, this one, 4 into 8, 32, minus of 7 into 5, that is 35. So this comes out to be minus 3, minus 2, and this is giving you 6 plus 12, and this then will give you minus 3 into 3, that is minus 9, and obviously it comes out to be 0. Hence proved that the given three vectors, they are coplanar. So this is a scalar triple product which tells you whether the vectors are coplanar or not. Now let's take the third numerical. In this numerical, we have to find out the projection of the vector A on vector B. To find out the projection vector of A, we use the formula A vector dot B vector divided by the magnitude square of the B vector multiplied by B vector. We know that when we take a dot product, it is basically the product of the magnitude of one vector and projection of the other vector on it. So we are using the same concept to find out this projection. So obviously in our case it is going to be 3i minus 4j plus 5k as A vector and dotted with 2i cap plus j minus k cap and divided by the magnitude of B. Magnitude of B is 2 square, that is 4, plus 1 minus 1 square is 1, and then it's to be taken square of it. Finally, we have to multiply it with B vector, which is 2i cap plus j minus k. So I just simply replace this A and B in this case. This now will become 3 multiplied by 2, that gives you 6, minus 4 with 1 will give you minus 4, 5 with minus 1 will give you minus 5, and this now will become root 6, but square of this will give you 6, and then we have 2i cap plus j minus k. If I simplify this, this comes out to be minus 3 by 6 of 2i cap plus j minus k. This is half, so this is going to be minus I cap plus half of j cap. Minus and minus will become plus. This is minus. Minus with this one will give you minus. Minus with this plus also will give you minus, and this one will give you plus half of k. So this is the projection of A on B. Let's take the fourth numerical now. And in this numerical, a scalar field is given to us in terms of the space coordinates. And we are required to find out the gradient of it. We know that when we have to get the gradient of phi, it means that nebula, that is I d over dx plus j d over dy plus k d of dz operated on the scalar field phi. So for our case, this becomes I d of dx plus j d of dy plus k d of dz multiplied by the field is 3x square y minus 2y square x. So let's first of all operate I cap d of dx on 3x square y minus 2y square x. Then we'll have j cap, partial derivative with respect to y, 3x square y minus 2y square x, and similarly the z component with partial derivative with respect to z, and that is again phi x square y minus 2y square x. Since we are dealing with a partial derivative, when I am taking the differentiation with respect to x, I will keep y as constant. Z is not there, so even if z was there, I will keep that as constant. So this now will become the partial derivative of the first term will give me 2 multiplied by 3, that is equals to 6 xy minus, this is x here, so this becomes 2y square plus j. Now the derivative with y will give me 3x square for the first term, 2 and 2 will make it 4 yx for the second term, k cap with z component. Since there is nothing of the z coordinate, so obviously this gives me 0. But we have to get the gradient of phi at the point given is 1, 2 and minus 1. So let's replace the values here. I, x as 1 and y as 2. 1 and 2, that gives you 12 minus 2 square 4 minus 2 multiplied by 2 8 plus j cap. X is 1, so giving me 3, 1 and this gives me 2, that is 0. So this finally will come out to be the gradient of phi, grad of phi is equals to 12 minus 8 will be 4i cap plus, and this 3 minus 8, that is minus 5j. So this is the grad of the given scalar field phi. Now let's take the fifth question. It's identity, and it's one of the very important identity which says that the gradient of 1 by r to the power n, we have to prove it is equal to this much, where r vector is basically the position vector of the point having a coordinate x, y, z. So its magnitude can be written as r square equals to x square plus y square plus z square. Therefore the r can be written as under root of x square plus y square plus z square. So if I replace it here, I will write this as gradient 1 by r to the power n as, for gradient I'll use the same, that is d over dx plus j dy over divided by dy plus k cap d over dz, the partial derivative. And if I replace r from that relation, this comes out to be 1 divided by x square plus y square plus z square to the power n by 2, because I am not using the under root in this case, so I am taking it out. So let's simplify it now. So this comes out to be I cap d of dx. Take it on the numerator, that will be helpful. This is x square plus y square plus z square to the power minus n by 2. And same you can do it with j cap d of dy x square plus y square plus z square to the power minus n by 2 plus k cap d of dz x square plus y square plus z square to the power minus n by 2. Now let's start the differentiation. As we know that when we are taking the partial derivative, I have to keep y and z constant. So this is nothing but is equals to I with negative sign the power n by 2, and within bracket I will get x square plus y square plus z square, that is minus n by 2 minus 1. The power is reduced by 1. So multiple of derivative of x square is equals to twice of x. Same I have to do for y and z component. Let me write that. This is n by 2 once again. X square plus y square plus z square to the power minus n by 2 minus 1 multiplied by twice of y. And similarly we'll go, this is plus here, plus k cap, and is n by 2 with a minus sign. Yes, this minus sign is there, and we'll also have the minus sign in this case also. Minus n by 2 x square plus y square plus z square to the power minus n by 2 minus 1 of twice of z. Now this 2 will go. This is minus n, the same story there. So we have something common. Let's take it out. It is x square plus y square plus z square to the power minus n by 2 minus 1. Then we have this n also common. Let me put it here with a negative sign. Whatever we have, that is the remaining part of it, can be written as xi cap yj cap plus zk cap. Let's take the simplified form of it. So this comes out to be 2 as common. So I'll write this as minus n. This is nothing but is equals to r square. R square, and let's take it this way. Minus n, 2 as LCM will give you minus 2 divided by 2. Right? And this is nothing but is equals to r vector. So if I take care of this 2 and 2, this will come out to be gradient of 1 by r to the power n is equal to, that gives me minus n. Take this in the denominator, this will come out to be r to the power minus n minus 2, and in the denominator this becomes negative, so this becomes n plus 2, and remaining is r vector. So this is our answer of the identity which is asked to be proved. Now let's take the sixth question. In this question, a vector is given to us and we are asked to find out its divergence and curl. So let's first of all calculate its divergence. Divergence of vector A, which is nothing but is equals to nebula dx plus j d of dy plus k d of dz, and is to be taken as a dot product of the vector A, x y square I cap minus 2x square y j cap plus y z square k cap. Since it is a dot product, so we have to multiply the respective components, that is I coefficient with I coefficient of the second vector, and this will be equals to d of dx of x y square minus d of dy of 2x square y plus d of dz of y z square. Since we are dealing with a partial derivative, so when I am doing the derivation with respect to x partial derivation, I will keep y square as constant and x derivative is 1 minus, this time we have to take a derivative with y, so this is equals to 2x square plus this will give me derivative with respect to z, that is 2yz. But we have to get the divergence of A at point 1 to n minus 1. So let's put the value. Y is 2, that gives me 4. X is 1, that gives me 2. And y is 2, but this is minus 1, giving me 4. So this comes out to be minus 2. That means the divergence of A at the given location is equals to minus 2. Now let's find out the curl of the vector A. Curl means that we have to take a nebula as a cross product of A. Now since it's a cross product, so this is written in this manner: I, J, K. Now the component of nebula, first of all, this is d over dx, d over dy, d over dz, and then the component of the vector A, x square y minus 2x square y, and finally this is y z square. Now if you simplify this, I leave this column, this row, take the y derivative of yz square. I am doing it directly. I think you can easily do it. Since we are taking the partial derivative, so y derivative is to be taken but z square to be kept as it is. So y derivative is 1 in this case. Now the derivative this way, we have to take a z derivative, but there is no z term here, so that gives me 0 minus j. Leave this column, and this row. Now you have to take a derivative of this term, and the derivative is with respect to x, since there is no x here, so that will give you 0. Then minus derivative of z is to be taken with this one, but once again there is nothing, so this gives me finally 0. Then the third one, k, that is leave this column and this row and take the x derivative, partial derivative. Since it's minus, this becomes minus 4yx, right? And then the derivative of y with this, with minus sign, so that is equals to 2xy. And if I simplify this, this is equals to z square I cap, this is out, and this gives me minus 6xy k cap. But we have to get the curl of A at position 1, 2 and minus 1. So putting z as 1, minus 1, square of it, that will give me 1, so I cap. But putting x as 1 and y as 2, that gives me minus 12k. So that is the answer for the second part of the question number 6. Now let's take the 7th question. Here we have to prove two identities. First one says that the curl of gradient of phi is always equals to 0. Let's take the first one. The curl of gradient of a scalar field can be written as I d of dx plus j d of dx dy and k cap d of dz, then crossed with same nebula dx plus j cap d of dy plus k cap d of dz, and finally it is operated on phi. Now this can be expanded as, since it is a cross product, we'll write this as I j k. Now when it's cross product, the second term is going to be, this is d of dx, d of dy, d of dz, and finally since it's operated on x, d of phi dx, d of phi dy, d of phi dz. Now if you notice that this row and this row, they have identical parameters. Even if you try to expand, you will find they will cancel out each other. Look at this. If I take this column and this row and take the derivative of this, this is d of dy, then with phi d square dz of phi minus this one, that is d square dy dz. This one is with this is the same one, so this is dy dz of phi plus, look, both these terms, they are same, identical. So finally they are going to give you 0, but let me write down all the terms. J, leave this one, so they have to multiply. So this is d square dx with dz minus this one, we have to take this one, so this is going to be once again d square phi over d x dz of phi. Then finally the k, leave this column and this one, so this is x and y, so d square dx dy of phi minus d square dx dy. So you can notice that all these terms, they come out to be 0. So hence always curl of gradient of a scalar field is equals to 0. Now let's take the second part of it. The second identity says that we have divergence curl of a vector field equals to 0. So divergence basically is with the scalar product. So we can write this as this one, divergence of curl of a vector, that is equal to I d of dx plus j d of dy plus k d of dz, and its dot product is to be taken with the curl of A. When we take the curl of A, this is basically I j k d of dx d of dy d of dz, and then ax ay az. Alright, so let's expand this. I d of dx I cap you write here plus j cap d of dy plus k cap d of dz, and that is to be taken a dot product with. Take this and this one, so this is I cap, When I take this one and this one, so I have to take a partial derivative of d of dy of az minus this is d of dz of ay, then minus j cap, leave this column, this row, this is d of dx of az minus d of dz ax plus k cap, and that is leaving this column and this row will give you d of dx of ay minus d of dy of ax. Now since it's a dot product, so in the dot product what we have to do, we have to multiply the respective values, means this is to be multiplied by this one. So if I do that, so this will become d square dx dy of az minus d dx dz of ay minus this one will give me derivative with y, d of dx dy of az minus, and minus now will become plus, so this is d of dy dz of ax. Then we go for this differentiation, that will give me d of dx dz of ay minus of d of dz dz dy of ax. Now you can check that in this particular case, this is d square, d square, d square, d square, d square also. This term will go with this one, and this negative term of ay will go with this positive term, this is out, and this positive term will go with this one. So all terms they will go, and finally we are going to get 0 for this. Now let's take the 8th numerical. In this numerical, a vector is given to us and they want us to prove that this is a solenoidal vector in this condition, that is x equals to 2z condition. For a vector to be solenoidal, its divergence must be equal to 0. That is I d of dx plus j d of dy plus k d of dz dotted with the vector a, that is y square z I cap minus twice zx j cap plus zx square k cap, that has to be 0. So when we have dot product, we have to multiply the respective components, and if we do that, this gives me d of dx of y square z minus d of dy of, this is 2z xy, y also is there, y, then we have d of dz of zx square, and that has to be 0. Since there is no x here, so its derivative is 0. With this one it will give me 2zx, and derivative with z here will give me plus x square, and that has to be 0. So for this to be 0, you must have x square equals to 2zx, 1x is out, so this is 2z, that is the condition required, and that is the answer, that this vector is solenoidal provided that we have x equals to 2z. Now let's take the ninth numerical, and in this numerical a force is given to us and we are asked to show it that this force is irrotational. When we say a vector field is irrotational, it means the curl of it must be 0. So let's check it. Let's take the curl of f. Curl means that we have to take it like this: I j k d of dx dy d of dz, and that is 2x minus 3y 4z. So if we expand it, leaving this column and this row, this is d of dy of 4z minus, and minus at this minus will become plus, so d of dz of 3y minus j. Leaving this column and that one, this will give me d of dx of 4z minus, this is dz of 2x plus k cap, and that is d of dx of minus 3y and minus d of dy 2x. Now you can very well see, since we are taking a partial derivative and there is no y term here, so its derivative is 0. This way this is z and there is no z here, even this is 0. We have to take a partial derivative with x and there is no x here. We have to take a partial derivative of z and there is no z here. And same is the story for these two terms also. So ultimately we are going to get 0 vector, which means the force is irrotational. This is your answer for the question number 9.